Today we've got 4 more examples of solving systems by substitution, and in this video we'll cover some of those special case things that can happen. So let's jump right in. This is exactly what we were doing in the first substitution video, just more practice. So in number 1, I see that I've got x plus 5y equals 4 and 3x plus 15y equals negative 1. So remember, one of our equations has to have one of the variables isolated. Either it needs to say x equals or y equals. So when I look at those two equations, the easiest variable to isolate is going to be this x that doesn't have a coefficient. Technically, you could isolate any variable, but if we can do less work, we might as well take advantage of that. So we're going to take that equation and we're going to solve it so that that x is by itself. And to do that, I just need to move the y to the other side of the equal sign. So to do that, I would subtract 5y. And that gives me x equals, I can just write it as 4 minus 5y. Remember, we don't actually do that subtraction because those are not like terms. The 4 is just a constant. The 5 has a y attached to it. You also could write this in the opposite order, negative 5y plus 4, if you prefer that. So now we're going to take that equation, and that's what we're going to substitute into our other equation. And in this case, we'll do that in place of x. So we're going to take this piece and substitute it into our other equation, which is 3x plus 15y equals negative 1. So I'm going to replace that x with the expression 4 minus 5y. So I have 4 minus 5y plus 15y equals negative 1. And now this is an equation that just has one variable, just the y, so we're going to get y by itself. I'm going to start by distributing that 3 to everything in the parentheses. 3 times 4 is 12. 3 times negative 5y is negative 15y. Still have that plus 15y equals negative 1. So now, next kind of logical flow for solving equations would be to combine any like terms. So I see on this left side of my equal sign, I have negative 15y plus 15y, which would make 0y. So that's just going to leave me with, we'll actually write that out. We'll say 12 plus 0y equals negative 1. And 0y is, of course, just 0. So what that's leaving us with is 12 equals negative 1. So now think back to when we solved equations. When we got something like this that doesn't make sense, we know 12 is not equal to negative 1, we say no solution. We can actually stop when that happens because there's not going to be an ordered pair at all that makes those lines intersect. And so what we actually know, if there's no solution, that means the lines never touch. These lines are parallel lines, is why that's happening. All right, let's try number 2. So it says we've got 6x plus 3y equals 54. You just need that first equal sign. That's a typo. And then 2x plus y equals 18. So again, when I'm deciding what variable I want to get by itself, I'm looking for one that doesn't have a coefficient. That's going to be the least amount of work. So this y would be the easiest thing to get by itself. So let's make that y isolated. We've got 2x plus y equals 18. To get y by itself, we would need to move the 2x, which we do by subtracting. And you can write this either as 18 minus 2x, or you can put the x first like we did when we were writing slope-intercept equations. For these equations, they don't need to be in slope-intercept form, so we don't have to do that. But if you're in that habit and you want to write that as negative 2x plus 18, that's totally fine. And now we're going to take that equation, and it says y equals. So in my other equation, the one we have not used yet, I'm going to substitute that in place of y. So I had 6x plus 3y equals 54. We need to replace that y with 18 minus 2x. So 6x plus 3, 18 minus 2x equals 54. And now we have an equation that just has x's, so we can solve it. Let's distribute first to get rid of the parentheses. So 6x plus 3 times 18 is 54. 3 times negative 2x is negative 6x equals 54. And now check this out. Again, when I'm combining like terms, 6x minus 6x would be 0x plus 54 equals 54. So 0x, of course, again, is just 0, so I get 54 equals 54. And now that statement, although a little weird in an equation, it is true. 54 does equal 54. So if you remember back when we did equations, when we get something that is equal on both sides, we call that infinite solutions. And so think about what we know about systems. That means that these two equations actually graph the same line. So if we graphed both of them, although the equations are written differently, they will produce the same line. And if you pay really close attention, check out that bottom equation. Every term in the top has been multiplied by 3. And that's why those equations work out to be the exact same, if you're curious. All right, number 3 is actually not anything super weird, but sometimes it does give students a hard time when we have two equations in y equals form. Or same thing if we had two equations in x equals form. It's going to look like we just set the equations equal to each other, but we can think about it the same way. So I'm going to use that top equation as my isolated version. And then I'm going to, in my other equation, y equals 2x minus 5, I need to replace just the y with what it's equal to in my highlighted equation, which was 4x minus 1. So when you have both variables solved like that, we're basically just setting them equal to each other, because we know if y equals 4x minus 1 and y equals 2x minus 5, then those two things also have to be equal. So to solve this one, I need to get my x's on the same side. I'm going to subtract 2x on both sides. That will give me 4x minus 2x is 2x minus 1 equals negative 5. I'm going to add 1 on both sides so that I have 2x equals negative 4. And finally divide by 2. X equals negative 2. So remember, we're not done yet. We still need to find what y is equal to. And we can actually take that point, and in this one, since both of the equations are isolated, you could use either equation. It does not matter. You'll get the same answer either way. But we're going to take that value, x equals negative 2, and we're going to substitute it in to, I'm going to use the top equation, the 4x minus 1. So we're going to replace that x with a negative 2. So 4 times negative 2 is negative 8. Negative 8 minus 1 is negative 9. So our point of intersection here would be negative 2, negative 9. And again, it's important to remember, write those as an ordered pair with the parentheses, comma in the middle, the x comes before the y. All right, I would encourage you at this point, and go ahead and give the video a pause. Try this problem, see how you do. Turn it back on and check your work. So we could solve for any of the variables, but it's going to be easiest to get that x by itself because the x does not have a coefficient other than 1. So if we're going to work with that equation, I'm going to say x minus 3y equals negative 2. And to get the x by itself, I need to move that 3y by using the opposite operation. So I add it on both sides. We get x equals, write this either as negative 2 plus 3y or 3y minus 2. Either one will work. So we're going to take that equation now that x is isolated, and we're going to substitute it into our other equation. We've got 10x plus 8y equals negative 20. And we need to replace the x because my isolated equation says x equals. So we've got 10. And in place of that x, I'm going to put negative 2 plus 3y, because that's what x is equal to, plus 8y equals negative 20. So now let's clear those parentheses by distributing. Multiply that 10. 10 times negative 2 is negative 20. 10 times 3y is 30y. Everything else stays the same. If I can combine like terms, I want to combine like terms. So 30y plus 8y is 38y. So I've got negative 20 plus 38y equals negative 20. And now I want to move that 20 to the other side. So then 38y, negative 20 plus 20 is 0. Now, don't let this throw you off. When you get something that's 0, if your variable still exists, if you still have that y there, we're still trying to isolate it. We're going to divide by 38. And that just tells me that my y value is 0. And that is something kind of unique that happens. It doesn't happen all the time, but it does not give you kind of a weird solution. So then we want to take that y equals 0 and substitute it in. It's going to be easiest if we use the isolated equation, the x equals negative 2 plus 3y. It's going to be the easiest one to use. So I need to replace the y with that 0. So x equals negative 2 plus 3 times 0. So 3 times 0 is just 0. And then negative 2 plus 0 is negative 2. So my solution here then would be negative 2, comma 0. We threw this example in here just to remind you, just because you get 0 somewhere doesn't mean you have no solution. And that's a common misconception. You can actually have 0 as an x or a y value in any of your answers. We will practice more in class with some of these special cases and then just some general examples. So make sure you go to class and ask your teacher questions if you need to.